Good morning, everyone. Welcome to the PhD seminar. Today, Giorgio and Chiara will present us their work about augmented and virtual reality, and more generally, the study of human perception of the scene.
Hello, everybody. My name is Giorgio Ballestin. I'm a second-year PhD student. I work with Fabio Solari and Manuela Chessa, and in the field of augmented reality, together with my colleague Chiara Bassano and Razino Sen. The topic of my project is achieving natural interaction in augmented reality environments. So I will start by giving you a quick overview on what I've done on the first year of PhD, which will introduce on what I am currently working right now. And then I will tell you what are my plans for future research. So as I said, my project is on how to achieve a natural interaction in augmented reality environments, which means is to try to understand if we can interact with an augmented reality interface, for example, in the same way that we can interact with physical ones. So for example, a smartphone, a tablet, or a computer. It is a relatively new field of study, which has several implications in other fields of studies. Some are more related with computer science in general, like computer graphics or computer visions. And there are other implications also on cognitive sciences like psychology, and also on biomechanics, ergonomics, and so on. The first way I started to work in this field was with a user research study where we wanted to see the perceptual differences when using different types of head-mounted displays. We used two different types of head-mounted displays. One was an optical see-through device, and the other was a video see-through device. The difference is that in an optical see-through device, the virtual augmentation is projected on top of transparent lenses, and you can see the real world through the transparent lenses. In a video see-through devices, on the other hand, you have a screen in front of your eyes, just like a virtual reality headset. And on the LCD monitors, you see the video stream of cameras which are placed behind your eyes, basically. Basically, the experiment was like in the picture. So the users had to perform a reaching task. They had to try to reach targets which were randomly appearing in a volume in front of the users. And when they performed the reaching task, we recorded the end positions, both in the headset's reference frame and externally with a connected device. We did two different tests. In the first case, we did not provide an internal feedback. The occlusion was not enabled, so the occlusion culling was disabled, basically. And in the second case, this internal feedback was provided again. This occlusion depth Q is very important to understand the relative distances in objects. So removing this Q was very important in the accuracy of during the tests. So the main research questions of these experiments were to see if the users were able to judge the 3D positions of the targets in the scene, and if they could interact properly with those objects, and if there were any noticeable differences between the two types of display. This is the data that we obtained, plotted in such a way that it can be considered as the top view of the previous scheme. So the user here is represented in the 0,0 position. The vertical axis is the depth, the distance from the user. The horizontal axis is left and right. The red dots represent the position where the targets appeared, while the blue dots are the hand position during the reaching trial. Here you can see how the clouds overlap with the real positions of the targets. And we saw that in general there was some level of depth compression, so depth underestimation in pretty much all cases, but you can see that in the video see-through device, especially when no internal feedback was provided, there was a severe depth underestimation. This is another representation of the same data. Basically, we obtain a linear fitting of all the trials by plotting the perceived distances on the vertical axis and the real position of the objects on the horizontal axis. So in the ideal case, all the trials should be on the bisector, because if it shows something, for example, at 10 centimeters, you should perceive it at 10 centimeters, and so on. So we use the slope of those linear fits to see what is the quality and the amount of the perception, the depth perception in that kind of experiment. There are 4 graphs because it's for the 2 different head-mounted displays, and there is the first case without the feedback and then with the feedback. We perform the same analysis for all the users. This is from all the data together, and then we did the same analysis for each user and obtained a normal distribution, displaying basically the performance in the different cases. The main problems that we encountered during that experiment was that the 2 head-mounted displays were not really it was not really a fair comparison, because the first one was a monocular device and the second one was a binocular device, and the disparity between views is a very strong depth Q. So it was expected that the video see-through device performed worse than the optical see-through. Also, the devices were not calibrated for each user, which can cause some level of distortions which cannot be imputed to the depth perception of the user, because it is simply an optical problem. Also, the Kinect, which was taking the measures, was not synchronized with the headset, so some data was noisy. We had to discard part of the data because it was also collected in noisy environments. And also, we did not have a control group, so it is not simple to say if part of the underestimation is due to biomechanical factors, for example, because maybe the target was very far away and you physically was unable to reach it because your arm is too short, or because of the optical properties and of perception aspects of the human. So my work right now is to perform again these experiments, but in a more controlled way. So by using 2 more similar devices, so both of them will be binocular, and each time a user performs the experiment, he will have to calibrate based on his own optical system, basically. The data acquisition system will be synchronized between the NEC and the devices, and also with the control group to work as a ground truth to remove the biomechanical factors out of the equations. So why do we need calibration of the devices? For the way augmented reality works, to place a virtual object in the scene, you need to know, you have to have an internal representation of the scene inside your system. And that internal 3D model of the scene must be ideally perfectly aligned with the real-world geometry. Also, in real time, the system must be able to compute the pose of the virtual camera to know what to render in your view. If the system is not properly calibrated, the pose estimation of the virtual camera is not providing a good 3D position, a good pose for rendering the correct imagery. Also, if the tracking system is based on a fiducial marker like this one, which is attached somewhere on the headset and not with the vision system, then you also need to compute the transformation matrix between the marker and your point of view. Otherwise, basically, the camera is considered, the virtual camera, which is the point from which everything is rendered, is considered as being on top of this marker. To calibrate the optical see-through device, we use the SPAAM technique, which is the single point active alignment method, simply because it is very used in augmented reality because it doesn't require a lot of hardware requirements. It just requires a tracker and a localization, a tracking localization system for that tracker. And it is easy to implement, hopefully. This is the scheme of the SPAAM technique. So we have, this is the vision system where the one tracker is attached solidly on the headset. Doesn't matter the position, but has to be rigidly attached to the headset. And the task basically is that the user is presented with a cross from inside the headset that we show with a shader, and he has to align that cross with another marker which is in the scene, and has to try to match the cross with the other marker. When the user feels that the crosshair is aligned, he presses a button, and the system saves several parameters. The parameters saved are the coordinates of the other tracker in the reference frame of the tracker that is placed on the headset, and then the pixel coordinates of the crosshair in that trial. What to do with those parameters? Let's see first how the system of the eye and the headset is modeled. This is usually the model which is used for the eye headset, which is an offset pinhole camera model, which basically is the projection model which maps 3D world points into the image plane coordinates. So the goal of the calibration is finding these 3x4 metrics, which allow us to map any point in the workspace into the image plane, basically lenses of the headset. The G metrics can be decomposed in this way in several other parameters, which are the intrinsic parameters of the camera and the extrinsic parameters. The intrinsic parameters are basically represents the physical properties of the optical system you are using. So we have the focal lenses, which are the distance from the image sensor usually, but in this case it is the human eye, and the image plane, which is the lenses. The skew factor basically causes a distortion in the image, and then we have the position of the pinhole from with respect to the camera center. Then we have the extrinsic parameters, which represents the pose of the marker which is attached to the headset with respect to the user eyes. We can rearrange that model to explicit the unknown parameters and obtain this system of equations. And the B matrix is constructed with the data that we obtain while collecting the alignments with the crosshairs. So every time we align one cross, two of those lines are added to the B matrix. So since we add two equations to the system of equations each time, and the G matrix is a 3x4 matrix, we need at least 6 alignments. Once we have these at least 12x12 matrix, we can solve to extract the G matrix from the singular value decomposition of the B matrix. Once we have this camera matrix with the projection model, we have to apply that projection to the camera, to the virtual camera in the graphic engine that we are using. Usually, however, the camera in graphic engines, the camera is modeled as a 4x4 matrix, while the matrix we obtain is a 3x4 matrix, just like in normal computer vision. So one way to use our obtained matrix in, like for example in Unity, is to either use an orthographics projection and push the parameters inside the projections, which is defined with the clipping planes of the view of the camera, Otherwise, my approach was to decompose the geometrics into its singular parameters and then apply those parameters singularly. So we decompose the matrix with RQ decomposition, which basically splits the 3x4 matrix into 3x3 upper triangular matrix and 3x3 orthogonal matrix. The only problem is that the RQ decomposition has not a singular solution. So, for example, if you change the signs of the first row and the first column of the two obtained matrix, you obtain by multiplying them again the same projection matrix, but if you then apply those different metrics to the projection, you obtain different results because maybe you have flipped axes. So there is some additional tinkering to do with the axes, and you have to study the geometry of the scene to see how the handedness of your system, of your coordinate system, and how the coordinate system of your model were oriented. Another problem with the calibration is the numerical instability of the result, because those computations assume that you are able to align perfectly the crosses with the marker in the scene. However, since, for example, you are breathing, maybe the marker is not very close, it is possible that you make some degree of error. So with only 6 alignments, it can be hard to achieve a very robust result, because even if you do very small drifts from the real positions, then the error accumulates over the computations, and then maybe you end up with like a 10 degrees angle differences, which can cause a misalignment with the real pose you are trying to find. So one solution was to use the ransack procedure to make the procedure more robust. So basically, how it works is that instead of using only 6 alignments, you take more, like for example 15, and then you start computing the model for the minimum amount of points that can be used for the SPAAM procedure. So in this case, it's 6 points. Once you compute the model, then you try to reproject all the original 15 points with the matrix you obtain, and then for each point you check the reprojection error. If the reprojection error is under a certain threshold, you can count that single point as an inlier. Otherwise, you discard it and count it as an outlier. Every time you find a model which basically justifies more inliers, then you save that model as the new best model, and you compute again the stopping criteria, because the stopping criteria is by number of iterations, but it is with a probabilistic approach. It is based on the probability of finding a better model than the one you have already found. So for example, if you have already 14 inliers in your model out of 15, it is very unlikely that you will find a better model. So the number of iterations will get reduced as your model improves over time. Another problem is that that calibration, after the calibration, basically you have the transformation between this tracker and your eye. The procedure has to be performed with one eye at a time. But if you want to use another tracking system, so for example in this HMD, this HMD has its own tracking system based on SLAM, which is performed with both a depth camera and a RGB camera. So if you want to use this tracking system, you have to find the transformation between this tracker and the reference frame for which this tracking system works. So one way to do it is to calibrate a camera which is attached rigidly to this tracker with the camera of the tracking system of the headset. So I calibrated this camera, which is attached rigidly to the headset, with the camera of the headset with the standard computer vision technique of taking pictures of checkerboards. And this is the final scheme of all the transformations that are in place. So this is the camera of the HMD, and here is the reference frame of the tracker. We want to find basically this transformation, which is the position from the transformation between the user eye and the tracking system of the reference frame of the tracking system of the headset. We get this transformation from the calibration, from the SPAAM procedure, and we obtain this transformation from calibrating the camera of the headset with the camera attached to this structure, which is 3D printed, and we have the CAD model of this. So this transformation can be extracted basically from the fact that the camera, which has been calibrated together with the other camera, is placed in a specific position in this structure. So by post-multiplying those two transformations, we obtain the transformation from the tracker to the reference frame of the tracking system of the headset. And then after the calibration with using this tracker, we can obtain the final transformation by post-multiplying all those two, the DH and the G metrics. So to show what is the result of a calibration, I used a mannequin which has the poor mannequin. I gauged his eyes off and put a stereo camera inside the mannequin. The stereo camera has baseline distances between the lenses, which is the same as the human average distance. And this is basically what happens when you have an uncalibrated setup. In this scene, inside the graphic engine, there was a sphere which was exactly aligned with the reference frame of this tracker. So if everything works properly, you should see a sphere moving rigidly with this tracker. But as you can see here, since in this case there was an axis flipped by 180 degrees, so basically the sphere is moving in opposite directions. But this is the simple case where only one axis is flipped of directions. It can be worse. So if there is a mix of translation, there are rotations which are wrong. When you move, you can see weird movements in the projections. This is the result after the calibration. So here there is the tracker, and you can see that if you move around the scene, the sphere remains aligned to the object in the real world. For the video see-through device, originally we were using the Google Cardboard, which is basically the smartphone which is placed on a headset, which is basically only a pair of lenses which splits the video feed from the camera behind the smartphone. This time we are going to use the Vive headset together with the same camera that was in the mannequin, the Z Mini. And also in this case I calibrated the Z Mini in the same way with the checkerboards like in standard computer vision. About the data acquisition, when we in the first batch of experiments we used the Kinect SDK to track the hand's position, but that proved to be a little bit noisy because the Kinect often fails to find the skeleton of the user, and the measures of the hand position can be noisy. So this time we are going to use a simple color tracking technique to extract the position of only the finger. In the original experiment, the original experiment was with the whole hand. So to increase a little bit the precision of the measurement, we are going to restrict the task to a pointing task. And here you can see in this image there is a green marker on the desk. So basically, what is happening is that the green color is segmented from the scene, and the 3D position of the finger in this case would be extracted from the scene. The problem about having a control group is that you have to display a 3D position in the space, which is the target for the reaching tentative, for the reaching trial. However, you cannot leave anything physical in the target position, because otherwise you simply touch the position and you have the material feedback that you actually reached the target position. So to account for this, we are going to do the experiments in a blind situation. So the room will be dark, and with basically there will be this structure, and a light will be shown, which is attached basically on a stick. So the experimenter puts the light in position with a remote controller. Starts the input, the perception input. Here, a light will turn on for a specific amount of time. When the LED turns off, the experimenter removes the stick, and then the test subject can then do the reaching tentative. So in this way, we can do the same thing with the augmented reality devices and remove the biomechanical aspects from the experiments. So, to sum up, my current research is mostly on perceptual aspects of augmented reality. We are working on the differences between different types of headsets, on the differences between using monocular and binocular vision, and on the different kinds of experiments that we can perform to get those data. And we believe that if we understand how we perceive the virtual images in a better way, then we can adapt to the systems to work better with what we perceive. So, for example, if we see that we consistently underestimated the depth, we can, for example, make a rendering technique which adapts the depth in a better way so that we can interact in a more easy way with augmented reality interfaces. So yes, we saw that there is some underestimation of depth for now during those kind of reaching tasks. And we are trying to replicate, however, those kind of experiments in a more controlled scenario with all the stuff I explained to you right now. And in the future, my plans for the future are in the near future, to start collecting the data with the setup I described to you. Once we have all the setup ready with all the calibration procedures set up and so on, we plan to use the same setup to do more experiments on perception. And afterwards, I will start to work on other aspects of augmented reality. So to improve the interaction with the hands by introducing an haptic glove for giving the haptic feedback, and also introducing a way to better localize the hand pose during the interaction, and also improve the environmental registration, which basically is the calibration of the localization of the pose of the virtual camera with respect to the real world, and how to obtain the 3D model and the 3D representation of the real world geometry, which is processed internally in the headset. And that is all for me. If you have any questions. Do you have any questions?
I think maybe at the end we will have some questions.
Okay.
Okay. Sorry, I have to check the button. Okay.
So today I'm going to talk about the bandwidth of human perception. As you know from your experience, we receive a lot of sensorial input from the environment surrounding us. And we are not able to process all these information. Just an example. For example, if I ask you, without looking at the person sitting beside you, what is the color of the shirt, you will think, who knows? And secondly, who cares? But this allows me to open a little parenthesis about attention. The majority of the information goes unnoticed if attention is not given to the information themselves. But if we can't process all of the information that we receive from the environment, how can we interact with it? How can we make action in the environment and so on? Because we have a system which is the working memory. The working memory is a cognitive system responsible for temporarily holding information available for processing. But working memory has two limits, in time and space. In fact, in working memory, information lasts 10-15 seconds unless we keep repeating the information. For example, when someone tells you a telephone number and you don't have a pen or a paper where to write, you start repeating in your head. And this allows working memory to last longer. The other limit is the capacity, so the number of information that we can actually remember. And we have two theories, the magical number 7 theory and the magical number 4 theory. They say that we can remember a limited number of elements defined as chunks. So chunks can be also cluster of information, not just digits or letters, but also words. And this depends also on the feature of the information which is in the cluster. In order to study the limit of working memory, one of the most common used tools are change blindness experiments. Change blindness is defined as the inability to see a change expected or unexpected between two different pictures when an interruption occurs or when the change is so gradual that it doesn't draw our attention. So attention always come back. Change blindness experiment can be done using pictures, videos, or a real-life experiment. In particular, if we consider pictures, we have two paradigms. The one-shot, which is the one I use when I replicate this kind of experiment in virtual reality, and the flicker one. In the one-shot, there is one image, blank, and a second image. While in the flicker, there is a loop. First image, blank, second image, blank, first image, and again and again. The first image is in general shown for 300 milliseconds because it's the time required to create a gist of the scene, so having a general representation of the scene, while the blank is in general from 0.02 to 9 seconds, and it masks the transient between the two images and without impairing the working memory. As a short example, okay, this is a flicker paradigm, which is in general is an example of experiment. C'est parti. Okay. You have to keep your eyes in the center and try to find the change. Okay. With focused attention, you probably noticed that the color of the pens have changed. In this case, they used a complex stimulus, but we can use also geometric stimulus. And also in this case, they wanted to find the sensibility to changing color, but we can study the sensibility to other kind of change. Appearance, disappearance, or a shifting, or a change in dimension. In this case, this is a video. I'm not sure this has been used for a study, but in videos, sorry.
Clearly, somebody in this room murdered Lord Smythe, who, precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
Okay. Didn't work, sorry. Okay. In video, what they do is exploiting the change in the viewpoint or gradual changes in order to see if people can find the change. In this video, there are 21 changes, and you can see it on YouTube if you are curious, if you have noticed all of them. But this is how experiment with video in general works. So, what is the pro of using images and videos? We can investigate the different aspects, as I said before, the color, the dimension, the shift. You can vary the complexity of the stimulus. We can use complex images or geometric images, lines, and so on. We can control the environment, and we can measure parameters. But on the other hand, if we look at a two-dimensional scene, we don't use the visual cues that we use in real life, perspective, stereopsis, and so on. So we don't know the effect of these cues on change blindness. And also the stimulus in general is delimited to 30-40 degree of the field of view, which is the foveal or parafoveal area, where images are more on focus. This is another experiment, instead, in real life. In real life experiment, there is a participant which is unaware. A person approaches him and asks for information. And while asking for information, this happens. And apparently 50% of the people are not aware of the change. So, change blindness apparently happens in daily experience, but the problem is that in this kind of experiment, they are difficult to control, it's difficult to measure objective parameters, and repetitivity are variable. This is why I decided to replicate experiment with change blindness in virtual reality, because in virtual reality I can control that parameter. So, on one hand, the goal of my experiment is understanding better human perception, considering different aspects, different tasks, but also the wideness of the space, the number of items, the spatial disposition of the object, the observation time, and the change applied. And use the results in order to have guidelines to design and implement application for example, training or simulation. If I want to give instruction to a person, how many instructions at once I can give to the person? How can I convey instruction to the person? So, now you will see the two different tasks for the one who didn't participate to the experiment. In the first case, we asked people if something has changed. So there was an image, a gray blank, and another image. And people had to answer if something had changed, pressing the trigger in the controller, yes or no. Well, in the where case, they had to indicate the position in which an item had appeared or disappeared, or they could press on the button using the raycast, or they could press the button equal if they hadn't seen no change, or they could wait for the 5 seconds pass and the new scene restart if they have perceived some change as there has been some change, but they haven't seen where. Oh, I forgot to say that in this condition, people had 150 milliseconds to answer. Considering the parameter, we had 3 different field of view. The one you see in violet is the field of view of the head-mounted display, while the one you see in light blue is the field of view where images elements were presented. So we use 40 degree, 80 degree, which basically corresponded to the field of view of the head-mounted display, and 120 degree. So in this case, people could see just a part of the scene, and they had to turn their head to see the entire scene. The spatial disposition were two, the vertical one, which was a sort of cylindrical, and the horizontal one. So, if we consider the top view, the, the element in the vertical case were in the internal side of the wall and were at the same distance from the user, while in the horizontal case they were on the table in the area between the two lines, and so had a radial disposition. Moreover, if we consider the vertical field of view, in the vertical case, it was constant, let's say. The objects were exposed at the same distance in 6 lines, while in the lateral view there were 6 different rays, and let's say that the angle is 30 degrees. But of course, if we project the angle on a vertical area or on an horizontal area, things change. We have to notice that there are some differences why we used the vertical and the horizontal layout, because, as I said before, in the vertical layout, objects are at the same distance, while in the horizontal layout, objects have varying distance from the user. There is perspective, and of course, even if the objects have the same size, the objects which are far from the user looks smaller. Objects were disposed in a sort of matrix. We divided this area and this area in bins of 5 degrees, while we divided this area and this area in 6 distance, or 8. So this is an example of how the experiment looked like, with the vertical layout for 40 degrees, vertical layout 80 degrees, and vertical layout 120 degrees. I took the video going a little bit backward, even if this wasn't allowed to participants, and they had to turn their head, actually. This is with the horizontal layout, 40 degrees, 80 degrees, and 120 degrees. Considering the observation time, as I said before, 300 milliseconds are the time required to create the gist of the scene. So we decided to use 2 times, 300 milliseconds and 900 milliseconds, which in the case of the smaller field of view, 40 and 80, wasn't a big difference because people could see at once what was in the scene. They had more time when they had 900 milliseconds to watch the scene, while in the case of 120 degree of field of view, when they had a short time for observation, they couldn't turn their head, so they just looked in a direction. While when they had more time, they could see the scene at least once. And this is with the vertical and with the horizontal. So, we considered 5 parameters: 2 observation time, 3 field of view, 2 spatial disposition, 5 number of item, and 3 types of change, which were appearance of an object, disappearance of an object, and no change, which was the control condition, actually. So in total, we had 180 conditions, and for each condition, we had 6 trials. For simplicity, we divide all these trials in 12 blocks. The order of the 12 blocks with chosen randomly, differently for one participant and another. And in each block, the order of presentation of the number of items was random, and the position of the object in the scene was random. But during the test, we recorded information about both the scene and the performance. So we can recreate each scene that had been shown. We know the position of the item, the kind of modification, and the position of the modified item. And we have information about people reaction, people performance. So head rotation and position, participant answer, the correctness of the answer, which is quite overlap, but I added it, and the reaction time, even if the analysis of reaction time didn't highlight any substantial difference. So the first analysis we did was on the percentage of correct answer. Here the data are divided based on the observation time and on the disposition. And as you can see, the percentage of correct answer decrease with the number of items in all the case. And we noticed, especially in the longer time trials, that the performances with 40 and 80 degree of field of view were comparable and were different with the one with the 120 degree. This is because with the smaller field of view, all the objects were visible, while in the second case, people had to turn their heads, so they had to update the image they are seeing and integrate all the image of the field of view. This is the analysis of the capacity. The capacity is defined as the number of items at which the accuracy falls under 80%. Here you see the total capacity, which comes from the sum of the capacity with add and remove. We excluded the control condition from this analysis. And what you can see confirm what I stated before, that performances with 40 and 80 degree are similar, while they are different to the performances with 120 degree. Also, if you consider the time, so here is short time, here is longer time of observation, performances, capacity is higher when people have more time to see the scene, which is coherent. Even if you see a difference between add and remove, these differences are not statistically significant. This is, we wanted to know how people behave during the trial. So for each participant, we wanted to analyze the rotation of the head during the trial. This is one trial, and this refers to the vertical condition and the short observation time, but all the trials are similar. So as you can see, we have the pitch, the yaw, and the roll, which are the rotation with respect to x, y, and z axis. And as you can see, with smaller field of view, we have no rotation because people don't have to rotate the head to see what they want to see in the field of view, in their field of view. While with 120 degree, there is a small rotation of the head, limited rotation of the head, and which is higher in the case of longer time. This is with short time, and this is with longer time. In this case, these two peaks you see is because people scan the scene from side to side. Scusatemi, dalla batteria scarica. Non ho sentito, Luca. Then we decided to go deeper in the analysis, and we tried to calculate the accuracy per beam. So, first of all, we calculated how much time each items appear in each of the beam I told you about before, which are these and these graph. Then we calculated the accuracy per beam. This is the 40-degree condition, and as you can see, when the number of items increase, the accuracy decreased. but there are no differences in the accuracy related to the position of item. This is the same for 80 degree. Again, accuracy decreased with the number of items. And this with 120 degree. Oh, I forgot to say that the red spot you see is where no items have appeared. This is the total. I mean, I calculated for each number of elements for 6, 8, and this is the sum of all the accuracy. For, again, the 40 degree of field of view, divided considering the observation time and the spatial disposition, so no difference. With the 80 degree of field of view, no difference. What surprised us was this difference. Short time of observation in the vertical and horizontal disposition. In the first case, you see that accuracy looks more uniformly arranged in the field of view, while in the second case you see a sort of white blob in the center. So we asked, we wonder why, if this was due to the behavior of participant or to the spatial disposition. So we started considering how people explored the scene, and we calculated the saliency. To calculate the saliency, we consider the rotation and the position of the head at each frame, and what was the center of the field of view the person was seeing, and so the portion of the scene that people could use. And also in this analysis, the only difference we can see is that if people have more time, they can explore more the scene than if people have lower time. But there is no difference between the vertical short time and the horizontal short time. So we decided to consider just the items that people could actually see and the accuracy on that items. And we obtained this for the vertical and this for the horizontal. We noticed this behavior, which is quite different. This means that in general, people tended to move their head more in the vertical case, not in the same trial, but between trial. Like I look a little bit the scene like this, then like this, which wasn't so common in the horizontal case. So we decided to recenter everything with respect to the center of the field of view, and which means...
What's the meaning of these colors?
This red is where no items were seen. This is, again, the number of items per each beam seen by the user. And this is the accuracy referred to this number of items.
But so the dark means that, what does it mean to be dark?
In this case, there could be 0 element or 10. Well, in this case, is referred to the accuracy from 0 to 1, normalized accuracy. So we recentered the item scene. So if I see an item and my rotation of the head is 0, it will be in the center, but if I am looking lateral and the item is there, again is 0 with respect to my field of view. And we obtained these two. And in this case, there is not that difference that I showed you before. There is not a central white blob distinguishing this from this. So that difference was simply due to the fact that people tended to move more in the vertical case. So in the end, what we found out was that accuracy decreased with the number of items and increased with observation time, confirming data from literature, that performances don't differ when objects were in the field of view. That if we consider the performances with the larger field of view, 120, recentered, they are similar comparable to the one with the field of view, 80 degree of field of view. That up now we have found no differences in the spatial disposition and between appearance and disappearance of object. But in future, what we want to do is considering the spatial arrangement of items and the position of the modified item with respect to the other one.
Do you have any questions?
I have one. I'm not sure that I understand how you can compute the accuracy, how you computed the accuracy before. My question is, if I don't see any object in a position, why my accuracy is 0?
Here, no.
No, I don't know.
This accuracy or
the last one. So the one in which here.
Here?
Yes.
Okay.
So if there is one black spot in the...
well, I think that this is a problem of core because it's dark gray actually. The items you didn't see were these red.
I see.
Yeah, I should use another scale because sometimes this is quite tricky.
That was my question.
And I have just a curiosity. But if you have an image and you have distances between objects,
yes.
Okay, is this distance preserved from our representation of the scene in the eye? I mean, the perception. I think there's something related to fovea.
Okay. You mean if I see two objects certain distance?
Yes, I'm thinking about the horizontal field of view.
Okay.
Okay. If I have I don't know, a distance which is depending on how far or close are things, do I see a sort of deviation or shrinkage of the scene?
There is a shrinkage due to your perspective. I mean, the near object are greater than the far object.
Okay.
In this case, object were sphere, so there were no other distortion in the image. I don't know if you intended this or...
No, probably, okay.
I mean, you understand that there is a relation between two objects.
Okay.
One is nearer than the other.
I was thinking if depending on the distance something changes or the dramatic changes.
Well, this was what we wanted to find. That with distance is added information with respect to the images. Okay. This is what we hoped to find and we haven't found that.
Okay. Thanks. Then thank you again.